Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the patient search for life's ancient whispers on Mars. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The wheels of perseverance turn with deliberate slowness across the rust-colored floor of Jezero Crater. Each revolution carries the rover another meter across terrain that once knew the gentle lap of water against stone. The 6 aluminum wheels, each nearly a meter wide, distribute the rover's weight across sediments that settled when Earth was still a violent nursery of colliding asteroids and volcanic outgassing. The crater stretches 45 kilometers wide, a bowl carved by cosmic impact 3.5 billion years ago, when Mars still wore clouds thick enough to cast shadows and rain fell from alien skies that glowed with the pale light of a younger sun. Here, where the ancient delta spreads its fingers of sediment like a frozen river mouth, the rover pauses with mechanical patience. Its instruments hum with quiet electricity, drawing power from a radioisotope thermoelectric generator that converts the steady decay of plutonium into the energy needed to keep this explorer alive in a world where solar panels collect only half the light they would gather on Earth. The thin atmosphere tastes of iron oxide and carries only whispers of the dense blanket that once wrapped this world in greenhouse warmth. When atmospheric pressure allowed liquid water to pool and flow across landscapes that now lie exposed to the brutal vacuum of space, the rocks beneath Perseverance's wheels hold stories written in layers that accumulated with the patience of geological time, mudstones and sandstones that settled grain by grain in waters that flowed for millions of years, carrying sediments from highland watersheds to this low-lying basin where they came to rest in the quiet depths of an ancient lake. Each stratum represents countless years of deposition, interrupted by periods of drought when the lake retreated and exposed its muddy margins to the slow work of erosion and oxidation. The finest clay particles, invisible to the naked eye, preserve chemical signatures of the water that once surrounded them, holding evidence of pH levels, salinity, and the complex chemistry of a world in transition. Scientists on Earth, separated by hundreds of millions of kilometers and radio delays that stretch each command and response across 20-minute intervals, guide this mechanical geologist through landscapes that mirror their planet's own violent youth. They search for biosignatures, chemical fingerprints left by organisms that might have thrived when Mars was young and wet, when methane rose from subsurface reactions and organic molecules assembled in tidal pools under skies that flickered with the aurora of a weakening magnetic field. The irony settles like dust across this ancient lakebed. Humanity's most advanced robot explores a world that died before complex life began on Earth, seeking evidence of microbial communities that may have flourished and faded while Earth's own oceans were still sterile and strange, dominated by simple bacteria that had not yet learned to harness sunlight or breathe oxygen. The Delta's stratigraphy reveals the biography of a dying world, each layer a chapter in the story of climate collapse. Near the base, where the oldest sediments lie buried beneath billions of years of accumulated dust and debris, researchers detect minerals that form only in the presence of liquid water clays and carbonates that crystallized when this crater held a lake deep enough to drown terrestrial mountains. Higher in the sequence, the rocks tell of increasing aridity, of seasonal floods that carved temporary channels before evaporating into the thinning atmosphere, leaving behind salt deposits and oxidized minerals that paint the landscape in shades of rust and ochre. Time moves differently here, measured not in heartbeats but in the half-lives of radioactive isotopes, not in seasons but in the slow drift of continents and the gradual cooling of planetary cores. The crater's rim, worn smooth by eons of thermal cycling and micrometeorite bombardment, stands as a monument to deep time, its rocks recording magnetic field reversals and atmospheric composition changes that occurred when Earth was still learning how to be habitable. The delta's rocks remember when this crater held a lake 300 meters deep, fed by rivers that carved channels still visible from orbit, their meandering paths frozen in stone like the fossilized tracks of some vast, slow-moving creature. Now only silence remains, broken by the soft whir of instruments and the patient click of cameras capturing images that travel across space at the speed of light, carrying Mars to human eyes that will never see this place directly. The rover's spectrometers peer into the atomic structure of rocks that have waited in darkness for billions of years, analyzing the chemical bonds between carbon and sulfur, between iron and oxygen, searching for patterns that might reveal the molecular machinery of life. Each measurement takes minutes to complete, the instruments working with the methodical precision of a librarian, cataloging the contents of a vast, silent archive. The search continues with mechanical patience, each sample a question posed to deep time, each measurement a whisper across the cosmos, asking the most profound question humanity has ever contemplated: were we ever not alone? The answer, if it comes at all, will emerge slowly from the accumulation of evidence, from the patient work of instruments that can detect organic molecules in concentrations measured in parts per billion, from the careful comparison of Martian geochemistry with the signatures of life preserved in Earth's oldest rocks. The silence of Mars keeps its secrets well, but humanity has learned to wait, to listen, and to look for truth in the spaces between certainties. The morning light of Sol 687 illuminates Perseverance's robotic arm as it extends toward a boulder the size of a terrestrial automobile, its surface pocked with tiny craters from billions of years of micrometeorite impacts. The arm moves with hydraulic precision, positioning the turret of instruments at its end like a surgeon preparing for delicate work. Within this mechanical appendage lies humanity's most sensitive chemical laboratory, miniaturized and hardened against radiation, capable of detecting organic molecules in concentrations so minute they would be invisible to any earthbound instrument from the previous century. The planetary instrument for X-ray lithochemistry begins its patient analysis, firing invisible beams into stone that crystallized when the solar system was young and chaotic. Each X-ray photon penetrates the rock's surface and excites atoms that have slept in darkness since before Earth's first continent emerged from primordial seas. The ejected electrons tell stories written in the language of quantum mechanics, their energy signatures revealing the presence of carbon, sulfur, nitrogen, the elements that form the backbone of terrestrial biochemistry. The spectrometer records these atomic whispers with digital precision, accumulating data points that will travel across interplanetary space to laboratories where scientists bend over printouts and computer screens, searching for patterns that might indicate life once stirred in Martian soil. Here, in a sample designated by the prosaic label Jezero-01, the instruments detect aromatic hydrocarbons, ring-shaped carbon molecules that on Earth often serve as the degraded remains of chlorophyll and other biological compounds. The molecules hide within the crystal lattice of ancient mudstone, protected from the harsh ultraviolet radiation that has sterilized Mars's surface for billions of years. Their preservation represents a minor miracle of planetary chemistry, organic compounds surviving the transition from a wet, protected world to the frozen desert that Mars has become. Their molecular bonds intact despite eons of thermal cycling and cosmic ray bombardment. The irony whispers through the data streams transmitted to Earth. These carbon signatures might represent nothing more than the products of volcanic outgassing or the decomposition of meteoritic organic matter, delivered by the same cosmic impacts that once made life's emergence so precarious. Yet the possibility remains. Encoded in the ratios of carbon isotopes and the patterns of molecular complexity, that these compounds once flowed through metabolic pathways in organisms no larger than the period at the end of this sentence. The uncertainty haunts the measurements like a gentle question mark, reminding researchers that extraordinary claims require extraordinary evidence, and that the universe delights in ambiguity. Deep within the mudstone matrix, sulfur compounds tell their own story of ancient chemistry. The Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals instrument, known by the acronym SHERLOC, fires laser pulses that cause organic molecules to fluoresce with characteristic wavelengths, their colors invisible to human eyes but perfectly recorded by digital sensors. The sulfur-bearing compounds suggest environments where microorganisms might have metabolized sulfate minerals, processing them through biochemical pathways that mirror the reactions occurring in Earth's deep-sea hydrothermal vents, where life thrives in eternal darkness, feeding on chemical energy rather than sunlight. The rover's drill core reveals stratification that speaks of seasonal changes in an ancient lake, layers of fine sediment alternating with coarser materials deposited during periods of higher flow. Each lamination represents perhaps a year in the life of Martian climate, recorded with the fidelity of tree rings in a world that never knew trees. The organic molecules appear concentrated in the finer layers, suggesting they settled from the water column during periods of calm, when hypothetical microorganisms might have bloomed in response to seasonal warming or nutrient influx, their microscopic remains drifting to the lake bottom like biological snow. The chemical analysis reveals another puzzle that keeps astrobiologists awake during long nights of data interpretation. The organic compounds show evidence of thermal alteration, their molecular structures modified by heat that occurred sometime after their initial formation. This thermal processing might have occurred during the burial and compression that turned lake sediments into stone, or perhaps during later episodes of volcanism that heated the crater's subsurface. The alteration complicates the search for biosignatures, as it becomes difficult to distinguish between the products of high-temperature geochemistry and the degraded remains of biological molecules. Yet within this complexity lies a strange comfort for researchers who understand that life on Earth has always been subtle, its signatures often ambiguous, and its evidence scattered across multiple lines of investigation. No single measurement will ever provide definitive proof of Martian biology, but the accumulation of compatible evidence organic molecules in the right chemical context, isotopic signatures that suggest metabolic processing, mineral associations that indicate habitable conditions begins to construct a circumstantial case that grows stronger with each carefully analyzed sample. The spectrometer continues its methodical work, measuring the abundance of trace elements that on Earth serve as micronutrients for living organisms. Molybdenum, zinc, vanadium elements that biological systems concentrate and process through enzymatic reactions. Their presence in the right proportions and chemical contexts provides another thread in the tapestry of evidence, another whisper from deep time suggesting that Jezero Crater once hosted the complex chemistry that bridges the gap between geology and biology. As Sol 687 fades into the salmon-colored sunset that marks each Martian day's end, the rover powers down its instruments and settles into the thermal hibernation that preserves battery life through the cold night. The organic molecules it has detected remain locked in stone, their secrets partially revealed but never fully surrendered, waiting with mineral patience for the next day's analysis to continue the slow conversation between human curiosity and cosmic mystery. In the laboratories of the Australian Centre for Astrobiology, researchers peer through electron microscopes at structures that formed on Earth 3.5 billion years ago, when the planet's atmosphere still tasted of methane and hydrogen sulfide. These ancient formations' stromatolites rise from Precambrian rocks like stone flowers, their layered architecture recording the patient work of cyanobacteria that built reef-like structures one microscopic filament at a time. The organisms trapped sediment and precipitated minerals in daily cycles, creating laminated domes that serve as Earth's oldest unambiguous evidence of life, their fossilized remains whispering across deep time about the possibility that similar structures might await discovery in the sedimentary rocks of Mars. Dr. Abigail Allwood adjusts the microscope's focus, examining the delicate layering that distinguishes biological stromatolites from their purely geological mimics. The genuine structures display a subtle asymmetry, a tendency toward branching and irregular growth that reflects the complex responses of microbial communities to changing environmental conditions. These biosignatures formed through the metabolic activities of organisms that had learned to harness sunlight, releasing oxygen as a waste product that would eventually transform Earth's atmosphere and pave the way for more complex life forms. The irony embedded in these ancient structures speaks to the patience required for evolutionary innovation. The very organisms that created Earth's first reefs also poisoned their anaerobic world with oxygen, triggering the first great extinction event in the planet's biological history. The stromatolites of Shark Bay, Western Australia, provide a living laboratory where researchers study the formation processes that might have operated on ancient Mars. In these hypersaline lagoons, cyanobacteria continue building layered structures through the same basic mechanisms that operated billions of years ago. Their metabolisms adapted to extreme salinity that would kill most terrestrial organisms. The modern stromatolites grow slowly, adding perhaps a millimeter of new material each year, their construction requiring decades to produce structures visible to the naked eye and centuries to create the dome-like formations that characterize ancient reefs. On Mars, the search for stromatolite-like structures requires instruments capable of detecting patterns that might be preserved in rocks that have endured billions of years of thermal cycling, radiation bombardment, and chemical alteration. The rover's cameras capture high-resolution images of rock faces where sedimentary layers reveal the ancient lake bottom's topography, searching for the characteristic doming and branching patterns that might indicate biological construction. Each promising formation requires multiple imaging angles and spectroscopic analysis to distinguish between structures formed by microbial activity and those created by purely physical processes such as wave action or sedimentary compaction. The mystery deepens when researchers examine Martian meteorites that have reached Earth, particularly the famous ALH 8001 specimen discovered in Antarctica's Allen Hills. Within this ancient rock, scientists have identified carbonate globules that contain organic compounds and magnetite crystals arranged in chains reminiscent of those produced by terrestrial magnetotactic bacteria. These microscopic organisms navigate Earth's magnetic field by incorporating iron oxide particles into specialized organelles, creating internal compasses that help them find optimal positions in aquatic sediments. The Martian magnetite chains display similar size distributions and crystallographic properties, suggesting they might represent the fossilized remains of organisms that once used Mars's ancient magnetic field for navigation, back when the planet still possessed a global dipolar field strong enough to deflect solar wind and maintain atmospheric pressure. Yet the debate surrounding ALH 8411 illustrates the challenge of identifying ancient life in extreme environments. The organic compounds might represent contamination from Antarctic ice or terrestrial biological activity that occurred after the meteorite's arrival on Earth. The magnetite crystals could result from high-temperature mineral precipitation during shock metamorphism, when the impact that ejected this rock from Mars subjected it to pressures and temperatures that rival those found in Earth's deep mantle. The uncertainty serves as a reminder that extraordinary claims require extraordinary evidence, and that the universe often presents researchers with phenomena that hover tantalizingly between biological and geological explanations. Perseverance's instruments approach this ambiguity with mechanical patience, analyzing rock textures at multiple scales to identify features that might represent fossilized microbial communities. The rover's microscopic imager captures details smaller than a human hair's width, revealing the internal structure of sedimentary layers where ancient organisms might have trapped and bound particles into distinctive patterns. The images travel across interplanetary space at light speed, carrying data that research teams analyze for evidence of the subtle asymmetries and branching patterns that characterize biological construction processes. In Jezero Crater's delta deposits, the instruments detect carbonate minerals that form through processes involving carbon dioxide and water, often precipitating around microbial communities that alter local pH conditions through their metabolic activities. These carbonate formations preserve microscopic textures that on Earth serve as windows into ancient ecosystems, their crystal structure recording information about water temperature, chemistry, and biological activity. The Martian carbonates display similar textures, though their interpretation requires careful consideration of alternative formation mechanisms that might produce analogous structures through purely geological processes. The search for Martian stromatolites represents a detective story written in stone, where researchers must distinguish between evidence and wishful thinking, between genuine biosignatures and the patterns that human minds tend to impose on ambiguous data. Each promising structure undergoes intensive analysis using multiple independent techniques, from high-resolution imaging to X-ray crystallography, building a circumstantial case that grows stronger with the accumulation of compatible evidence. The work proceeds with the methodical care of archaeologists excavating a delicate site, knowing that hasty conclusions might obscure the truth they seek to uncover. As the rover continues its exploration of ancient lake bed sediments, it carries with it the accumulated wisdom of terrestrial stromatolite research, the knowledge that life's signatures can persist across billions of years if preserved in the right chemical and physical environments. The question remains suspended like dust in the thin Martian atmosphere: did microbial communities once build layered structures in the shallow waters of Jezero Crater, leaving behind fossilized evidence that still awaits discovery in rocks that have kept their secrets through the long, slow death of a world? 4 billion years ago, Mars possessed a magnetic field that wrapped around the planet like an invisible shield, generated by convection currents in a molten iron core that churned with the heat of planetary formation. This magnetosphere deflected the charged particles of solar wind, protecting a thick atmosphere that allowed liquid water to pool in vast oceans and networks of rivers that carved the landscapes still visible from orbit today. The magnetic field lines stretched into space like the ghostly fingers of a cosmic hand, creating a protective bubble that preserved atmospheric pressure and enabled the complex chemistry necessary for life's emergence and persistence. But planetary cores are mortal things, and Mars, being smaller than Earth, radiated its internal heat more quickly into the vacuum of space. The thermal engine that drove the dynamo began to falter as the planet's interior cooled below the critical temperature needed to sustain convection in liquid iron. Somewhere between 3 and 4 billion years ago, the magnetic field weakened and collapsed, leaving Mars naked to the solar wind's erosive power. Without magnetic protection, the atmosphere began its slow hemorrhage into space, molecule by molecule, as charged particles stripped away the gases that had once supported rivers, lakes, and possibly life itself. The transition occurred with geological patience, unfolding over hundreds of millions of years as atmospheric pressure gradually decreased and surface water began to boil away into the thinning air. Rivers that had flowed for millions of years turned intermittent, then seasonal, then disappeared entirely, except during brief periods when volcanic outgassing or asteroid impacts temporarily thickened the atmosphere enough to allow liquid water's return. Lakes that had persisted for epochs began to evaporate faster than tributary streams could replenish them, leaving behind salt deposits and mineral concentrations that tell of increasing salinity as available water became ever more precious. The mineralogy preserved in Martian rocks records this atmospheric collapse with chemical precision. Early in Mars's history, when thick air provided greenhouse warming, surface rocks formed under conditions of neutral pH and moderate oxidation, creating the clay minerals and carbonates that require liquid water for their formation. As the atmosphere thinned and temperatures dropped, the surface chemistry shifted toward more extreme conditions, producing sulfate minerals and iron oxides that paint the modern landscape in shades of rust and ochre. These chemical signatures serve as a timeline of planetary death, each mineral assemblage marking another step in the transformation from a potentially habitable world to the frozen desert that greets human exploration today. The irony embedded in this planetary biography speaks to the delicate balance required for long-term habitability. Earth maintains its magnetic field through the continued convection of its larger iron core, a thermal engine sustained by radioactive decay and the gradual cooling of primordial heat. Our planet's magnetic field has reversed many times throughout geological history, occasionally weakening to a fraction of its current strength. Yet, it has never completely collapsed as Mars's field did billions of years ago. The difference in planetary mass Earth contains 10 times more material than Mars proves decisive in determining which worlds can maintain the protective magnetic environments necessary for atmospheric retention and surface habitability. Evidence of Mars's magnetic past remains frozen in the planet's crustal rocks, particularly in the ancient terrains of the southern hemisphere where remnant magnetization records the orientation and strength of magnetic fields that existed when the rocks crystallized from cooling magma. These paleomagnetic signatures, detected by orbiting spacecraft equipped with sensitive magnetometers, reveal that early Mars possessed a global magnetic field comparable in strength to Earth's current magnetosphere. The magnetic stripes preserved in Martian crust resemble the patterns found at Earth's mid-ocean ridges, suggesting that Mars once experienced plate tectonics and seafloor spreading, geological processes that require substantial internal heat and convective circulation. Perseverance's instruments detect the consequences of atmospheric loss in every sample they analyze. The oxidized iron that gives Mars its rusty color formed when water vapor, stripped from surface reservoirs by the departing atmosphere, broke apart in the upper atmosphere and left oxygen behind to react with surface rocks. This oxidation occurred over geological timescales, requiring millions of years to produce the iron oxide concentrations visible today. The process represents a planetary-scale chemical reaction, driven by the slow death of atmospheric protection and the inexorable exposure of surface materials to cosmic radiation and extreme temperature fluctuations. The loss of atmospheric pressure created a cascade of environmental changes that transformed Mars from a potentially habitable world into a cosmic refrigerator. Without thick air to trap and redistribute heat, surface temperatures began fluctuating wildly between day and night, summer and winter, creating thermal stresses that gradually fractured exposed rocks and broke down the mineral structures that had formed under more stable conditions. Permafrost crept deeper into the subsurface as the average temperature dropped below water's freezing point, locking away much of the planet's remaining water in underground ice deposits that persist to this day. Yet, the atmospheric collapse might not have been uniform or instantaneous across the planet's surface. Some researchers propose that local magnetic anomalies, particularly in the southern highlands, might have provided temporary refuges where atmospheric pressure remained elevated for millions of years after the global field collapsed. These magnetic umbrellas could have sheltered small regions where liquid water persisted in isolated lakes and groundwater systems, creating oases of habitability that might have sustained microbial communities long after most of the planet became uninhabitable. The question haunts the geological record preserved in Jezero Crater's sediments: did life on Mars have time to establish itself before the magnetic field failed? And if so, could organisms have adapted to the slowly changing conditions as their world died around them? The answer lies hidden in the chemical signatures and mineral assemblages that Perseverance analyzes with patient precision, searching for evidence of biological activity that might have occurred during the critical transition period when Mars transformed from a potentially living world into the silent monument to planetary mortality that orbits the Sun today. As the rover continues its exploration, it carries instruments capable of detecting the subtle isotopic signatures that might reveal whether life persisted through Mars's atmospheric collapse, perhaps retreating into subsurface environments where liquid water and chemical energy sources remained available even as the surface became increasingly hostile to biological activity. The drill bit penetrates ancient mudstone with mechanical persistence, its tungsten carbide teeth grinding through rock that solidified when Mars still possessed flowing rivers and seasonal weather patterns. Each rotation carries the bit deeper into sediments that accumulated grain by grain in the quiet depths of Jezero Crater's lake, where fine particles settled through water columns that may have teemed with microscopic life. The drilling process generates heat that could destroy organic molecules, so the operation proceeds with careful temperature monitoring, the bit advancing in measured increments to preserve the chemical integrity of samples that have waited 3.5 billion years for analysis. The hollow core that emerges from the borehole represents a journey through deep time, its layered structure recording environmental changes that occurred as Mars transitioned from a wet, potentially habitable world to the frozen desert visible today. Near the top of the core, oxidized minerals tell of exposure to atmospheric oxygen and cosmic radiation, while deeper sections preserve the chemical signatures of more reducing conditions that existed when thick air protected the surface from space-based weathering. The core's diameter measures precisely 7 millimeters, Yet within this slender cylinder lies compressed the history of an entire world's climatic evolution. Dr. Kenneth Williford, the deputy project scientist for the Mars Sample Return mission, studies similar drill cores extracted from Earth's oldest sedimentary formations, where microbial life left chemical fingerprints that remained detectable after billions of years of geological processing. In the Pilbara region of Western Australia, ancient mudstones preserve organic compounds and isotopic signatures that provide evidence of biological activity from Earth's earliest epochs, when the planet's atmosphere contained little oxygen and life consisted of simple prokaryotic organisms that thrived in environments similar to those that might have existed on early Mars. The Martian mudstone reveals its secrets slowly through spectroscopic analysis that can detect organic molecules in concentrations measured in parts per million. These carbon-based compounds, if biological in origin, would represent the degraded remains of cellular structures that once mediated the chemical processes of life, lipid membranes that controlled molecular transport, protein fragments that catalyzed biochemical reactions, or nucleic acid components that stored genetic information. The challenge lies in distinguishing between organic matter that might have biological origins and similar compounds produced through non-biological processes, such as volcanic outgassing or meteoritic delivery. Within the drill core, researchers detect sulfur-bearing organic compounds that on Earth often result from bacterial metabolism of sulfate minerals, a process that occurs in environments ranging from deep-sea hydrothermal vents to underground aquifers where sunlight never penetrates. These sulfur signatures suggest chemical conditions that might have supported chemosynthetic organisms, microbes that derive energy from inorganic chemical reactions rather than photosynthesis. The kind of life that might have thrived in Mars's subsurface even as surface conditions became increasingly harsh. The irony whispers through the laboratory data streams humanity's most sophisticated analytical instruments struggle to definitively identify signs of life that might have been abundant enough to alter planetary chemistry, yet remained microscopic and ephemeral enough to leave only subtle traces in the geological record. The organic molecules detected in Martian mudstone exist at the threshold of analytical detection, their concentrations so low that each measurement requires careful calibration and multiple confirmatory analyses to distinguish genuine biosignatures from instrumental noise or terrestrial contamination. Deeper in the core, the drill encounters layers that formed during seasonal cycles in the ancient lake, alternating bands of fine and coarse sediment that record changes in water flow and sediment delivery that occurred with Martian orbital periodicity. These laminations preserve evidence of environmental conditions that changed over timescales relevant to biological adaptation, suggesting that if life ever established itself in Jezero Crater, it would have experienced regular variations in temperature, chemistry, and nutrient availability that might have driven evolutionary innovation and metabolic diversification. The chemical analysis reveals trace elements that serve as biological nutrients, phosphorus that forms the backbone of energy-storing molecules like ATP, sulfur that participates in protein structure, iron that enables electron transfer in metabolic pathways. These elements appear in ratios and chemical associations that mirror those found in Earth's oldest biologically influenced sediments, though the patterns remain ambiguous enough to permit non-biological explanations. The uncertainty reflects the fundamental challenge of astrobiology. Life's chemical signatures often overlap with those produced by purely geochemical processes, requiring researchers to build circumstantial cases based on the accumulation of compatible evidence rather than definitive proof. The drilling operation represents a form of planetary archaeology, where researchers excavate through layers of compressed time to reach sediments that formed during Mars's most potentially habitable period. Each sample provides a snapshot of environmental conditions that existed during a specific interval in the planet's climatic history, allowing scientists to reconstruct the sequence of changes that transformed Mars from a world of lakes and rivers into the desiccated landscape explored by robotic vehicles today. The mystery embedded in the mudstone cores extends beyond the question of past life to encompass the broader puzzle of planetary habitability and the conditions necessary for biological emergence and persistence. The organic compounds detected by Perseverance's instruments exist at concentrations that suggest either very sparse biological activity or very efficient degradation processes that have erased most traces of once abundant life. Both possibilities carry implications for understanding how common life might be in the universe and how detectable its signatures remain after billions of years of planetary evolution. As the rover continues its methodical sampling of Jezero Crater's sedimentary deposits, it constructs a growing archive of materials that will eventually return to Earth for analysis with instruments too large and complex to send to Mars. These future investigations will push the boundaries of analytical chemistry, searching for isotopic signatures, molecular fossils, and mineral textures that might finally resolve the question of whether life once stirred in the sediments that now sleep beneath the Martian sky. Their secrets locked in stone, but not yet surrendered to human curiosity. The tunable laser spectrometer aboard the Curiosity rover detects methane in the Martian atmosphere with concentrations that fluctuate like a planetary heartbeat, rising and falling with seasonal regularity that puzzles researchers attempting to understand the source of this simplest hydrocarbon molecule. During northern summer, methane levels climb to nearly 10 parts per billion, a concentration barely detectable by Earth's most sensitive instruments, yet significant enough to suggest active processes occurring somewhere beneath Mars's frozen surface. In winter, the concentrations drop to undetectable levels, creating a mystery that has persisted through multiple mission cycles and hundreds of atmospheric measurements. On Earth, methane originates primarily from biological processes, the metabolic waste products of bacteria that thrive in oxygen-free environments ranging from cattle digestive systems to anaerobic sediments in wetlands and lake bottoms. These methanogenic organisms represent some of life's most ancient lineages, prokaryotes that learn to extract energy from simple chemical reactions involving carbon dioxide and hydrogen, producing methane as a byproduct of their cellular metabolism. The process occurs wherever organic matter decomposes in the absence of oxygen, creating the natural gas deposits that humans extract for energy and the atmospheric background that contributes to greenhouse warming on a global scale. Yet methane can also form through purely geological processes that require no biological involvement whatsoever. Serpentinization reactions occur when water interacts with iron-rich minerals in the presence of heat, producing hydrogen gas that subsequently reacts with carbon dioxide to form methane through catalytic processes involving metal surfaces. These reactions occur at hydrothermal vents on Earth's ocean floor, where superheated seawater percolates through basaltic crust and emerges as mineral-rich solutions that support unique ecosystems despite their chemical toxicity and extreme temperatures. The seasonal variation in Martian methane concentrations suggests a source that responds to temperature changes, possibly through thermal cycling that affects the rate of subsurface chemical reactions or the efficiency of methane transport from underground reservoirs to the surface atmosphere. During warmer months, increased thermal energy might accelerate geological processes that produce methane, or enhanced sublimation of subsurface ice might carry trapped methane molecules to the surface where atmospheric instruments can detect their presence. The irony embedded in these measurements speaks to the fundamental challenge of interpreting ambiguous evidence. The same molecule could represent either the waste product of living organisms or the result of purely chemical processes occurring in Mars's hidden subsurface. Dr. Christopher Webster, who leads the methane detection efforts at NASA's Jet Propulsion Laboratory, compares these atmospheric measurements to trying to detect the scent of a single flower in a football stadium filled with scentless air. The concentrations hover at the absolute threshold of instrumental detection, requiring sophisticated calibration procedures and multiple confirmatory measurements to distinguish genuine methane signals from instrumental artifacts or terrestrial contamination. Each positive detection undergoes rigorous analysis to eliminate possible sources of error, from temperature-dependent instrumental drift to cosmic ray interactions that might produce spurious signals in sensitive electronic detectors. The European Space Agency's Trace Gas Orbiter adds another layer of complexity to the methane mystery by failing to detect the molecule during simultaneous measurements with surface-based instruments. The orbital spectrometer, designed specifically to map trace gases in the Martian atmosphere, should easily detect methane at the concentrations reported by surface rovers, yet its measurements consistently return null results that contradict the positive detections made at ground level. This discrepancy suggests either that methane sources are extremely localized, producing detectable concentrations only in specific geographic regions, or that the measurement techniques themselves are subject to systematic errors that researchers have not yet identified. The temporal pattern of methane detections reveals another puzzle that challenges simple explanations. Rather than showing steady background concentrations punctuated by occasional spikes, the measurements display what researchers describe as burst events, sudden increases in methane abundance that last for hours or days before returning to baseline levels. These events suggest active sources that release methane episodically, possibly triggered by geological processes such as thermal cycling, tectonic stress, or the seasonal migration of subsurface water that might mobilize trapped gases and transport them to the surface. Underground reservoirs might store methane produced during earlier epochs in Mars's history, when environmental conditions were more favorable for either biological or geological methane production. These ancient accumulations could remain stable for millions of years in subsurface ice or mineral formations, only to be released when seasonal temperature changes create fractures in permafrost layers or alter the equilibrium conditions that keep gas molecules bound to solid surfaces. The release mechanism might operate like a planetary respiratory system, inhaling and exhaling methane in response to orbital cycles and climatic variations that occur over timescales much longer than human observation periods. The search for methane's source has led researchers to examine Mars's geological history for evidence of processes that might generate hydrocarbon molecules through non-biological pathways. Ancient impact craters might have created hydrothermal systems that persisted for thousands of years after formation, providing the heat and chemical conditions necessary for methane synthesis through reactions between water, carbon dioxide, and iron-rich minerals. Volcanic activity, though largely dormant today, might continue at low levels in subsurface magma chambers that maintain elevated temperatures and drive chemical reactions capable of producing trace gases that eventually reach the surface through fracture networks and permeable rock formations. The mystery deepens when researchers consider the atmospheric chemistry that should destroy methane molecules within a few hundred years of their release into the thin Martian atmosphere. Ultraviolet radiation from the sun breaks apart methane through photochemical reactions that should eliminate any trace of the molecule unless sources continuously replenish atmospheric concentrations. This rapid destruction rate means that any methane detected in today's atmosphere must originate from recent geological or biological activity, narrowing the temporal window for possible source mechanisms and increasing the significance of positive detections for understanding contemporary processes on Mars. The isotopic composition of carbon atoms locked within Martian organic molecules tells stories that unfold at the scale of individual nuclei, where the presence or absence of a single neutron can reveal whether biological processes once operated in the ancient sediments of Jezero Crater. Carbon-12 and carbon-13 isotopes that differ only in nuclear mass participate differently in the metabolic pathways of living organisms, creating subtle but measurable preferences that persist in organic matter long after the organisms themselves have decomposed into constituent atoms. These isotopic signatures serve as molecular fossils, preserving evidence of biological activity and chemical ratios that can survive billions of years of geological processing. On Earth, photosynthetic organisms preferentially incorporate the lighter carbon-12 isotope into their cellular structures, discriminating against carbon-13 through enzymatic processes that favor molecules with lower atomic masses. This biological preference creates organic matter enriched in carbon-12 relative to the atmospheric carbon dioxide from which it derives, establishing isotopic signatures that remain detectable in petroleum, coal, and ancient sedimentary organic matter. The enrichment typically ranges from 20 to 30 parts per thousand, a small but consistent deviation from inorganic carbon sources that serves as one of geology's most reliable indicators of past biological activity. The sample analysis at Mars Instrument aboard the Curiosity rover has detected organic compounds in Gale Crater mudstones with carbon isotopic compositions that fall within the range produced by biological processes on Earth. though the values also overlap with those generated by non-biological chemical reactions involving atmospheric carbon dioxide and volcanic gases. The ambiguity reflects the fundamental challenge of using isotopic evidence to identify ancient life, while biological processes create distinctive isotopic signatures. Purely chemical reactions can sometimes produce similar patterns through mechanisms that involve no living organisms whatsoever. Dr. Jennifer Eigen-Brody, a biogeochemist at NASA's Goddard Space Flight Center, compares the search for biological isotopic signatures to archaeological detective work, where researchers must distinguish between artifacts of human activity and naturally occurring objects that coincidentally resemble cultural materials. The carbon isotope ratios measured in Martian samples hover in the borderland between biological and geological explanations, requiring additional lines of evidence to support either interpretation. The uncertainty embedded in these measurements speaks to the subtle nature of life's chemical fingerprints and the sophistication required to detect them in rocks that have endured billions of years of thermal and chemical alteration. The isotopic analysis reveals another layer of complexity in the sulfur-bearing organic compounds detected throughout Martian sedimentary rocks. Sulfur isotopes provide an independent measure of biological activity, as certain bacteria preferentially process lighter sulfur, 32 over heavier sulfur 34, when metabolizing sulfate minerals for energy. These sulfur-reducing organisms thrive in oxygen-free environments where they use sulfate as an alternative to oxygen for cellular respiration, producing hydrogen sulfide as a waste product and leaving behind organic matter enriched in the lighter sulfur isotope. The Martian sulfur signatures display isotopic compositions that could result from either biological sulfate reduction or high-temperature chemical reactions that occur during volcanic processes or thermal metamorphism. The overlap between biological and geological sulfur isotope signatures illustrates the challenge facing astrobiologists who must account for all possible formation mechanisms before concluding that isotopic evidence supports the former presence of life. The irony whispers through these measurements like an echo of cosmic uncertainty. The very processes that might have supported life on ancient Mars could also produce chemical signatures indistinguishable from those created by purely geological phenomena. Nitrogen isotopes add another dimension to the search for biological signatures, as these atoms participate in the protein synthesis and nucleic acid formation that characterize all known life forms on Earth. Biological nitrogen fixation. The process by which organisms convert atmospheric nitrogen gas into ammonia for cellular use creates isotopic fractionations that can persist in sedimentary organic matter for billions of years. The nitrogen isotope ratios measured in Martian samples fall within ranges that could indicate either biological processing or atmospheric chemistry involving nitrogen compounds that underwent photochemical reactions in the upper atmosphere. The interpretation of isotopic evidence requires careful consideration of the thermal history experienced by Martian organic matter since its formation. Heat can alter isotopic compositions through processes that preferentially release lighter isotopes from molecular bonds, creating artificial enrichments that might be mistaken for biological signatures. The mudstones of Jezero Crater show evidence of thermal alteration that occurred sometime after their initial formation, possibly during burial and compression or during later episodes of igneous activity that heated the subsurface. This thermal processing complicates the isotopic record and requires researchers to model the effects of temperature and time on the preservation of original isotopic signatures. Advanced mass spectrometry techniques planned for future Mars sample return missions will provide isotopic measurements with precision far exceeding anything possible with current robotic instruments. These Earth-based analyses will examine isotopic compositions at the scale of individual organic molecules, using techniques such as secondary ion mass spectrometry and ramped pyrolysis to isolate specific compounds and determine their isotopic signatures with uncertainties measured in tenths of parts per thousand. Such precision might finally resolve the ambiguities that currently surround the interpretation of Martian carbon, sulfur, and nitrogen isotope data. The isotopic alphabet written in Martian organic matter represents a form of molecular archaeology, where researchers reconstruct ancient biological and chemical processes from the statistical distributions of atomic nuclei that have survived in sedimentary rocks for geological ages. Each isotopic measurement provides a piece of evidence that must be integrated with mineralogical, morphological, and chemical data to build comprehensive models of past environmental conditions and the processes that might have operated in ancient Martian ecosystems. The search for isotopic biosignatures continues with the patient accumulation of measurements that gradually constrain the possible explanations for organic matter preservation in Martian sediments. Whether these signatures ultimately point toward biological or geological origins, they provide invaluable insights into the chemical processes that operated on early Mars and the environmental conditions that might have supported life during the planet's most potentially habitable period, when liquid water flowed across landscapes that now lie silent beneath alien skies. The mineral assemblages preserved in Jezero Crater's sedimentary deposits read like a chemical diary of ancient hydrothermal activity, where heated groundwater once percolated through subsurface rock formations and emerged at springs that bubbled with dissolved minerals and gases. Silica terraces cascade down the crater's inner walls in fossilized formations that mirror the hot spring systems of Yellowstone National Park, their layered structures recording thousands of years of mineral precipitation from waters that reach temperatures approaching the boiling point. These thermal features represent some of Mars's most promising targets for astrobiological investigation, as hydrothermal environments on Earth support diverse microbial communities that thrive in conditions of extreme temperature and chemical toxicity. The X-ray crystallography data transmitted from Perseverance's instruments reveals the presence of opaline silica, a hydrated form of silicon dioxide that forms when silica-rich water cools and precipitates its dissolved mineral content in environments where temperatures fluctuate around 60 to 80 degrees Celsius. This temperature range falls within the tolerance limits of hyperthermophilic bacteria on Earth, organisms that represent some of life's most ancient lineages and might provide analogs for the types of microorganisms that could have colonized Martian hot springs during the planet's early history, when geothermal energy remained abundant and surface water maintained liquid state despite cooling atmospheric conditions. Dr. Kathleen Benison, a geochemist specializing in extreme environment mineralogy, studies similar silica formations in Australia's Pilbara region, where ancient hydrothermal systems preserved evidence of microbial activity from 3.5 billion years ago. The terrestrial deposits contain microscopic textures and chemical signatures that indicate biological involvement in mineral precipitation processes, as organisms modified local pH conditions and provided nucleation sites for crystal formation. These biosignatures survive in the rock record despite billions of years of weathering and thermal alteration, demonstrating that evidence of hydrothermal life can persist across geological timescales if preserved in the right mineralogical context. The Martian silica deposits display internal structures that suggest rapid precipitation from supersaturated solutions, possibly during periods when hydrothermal activity intensified due to volcanic heating or geothermal circulation driven by residual planetary heat. The textures preserved in these formations indicate that mineral-rich water flowed through fracture networks in the subsurface before emerging at springs, where rapid cooling caused dissolved silica to precipitate in concentric layers around discharge points. The resulting terraces preserve information about water chemistry, temperature gradients, and flow rates that existed when Mars still possessed active hydrothermal systems. Salt deposits discovered throughout the crater's sedimentary sequence provide additional evidence of evaporative environments where briny water concentrated dissolved minerals through solar heating and atmospheric desiccation. The mineralogy of these evaporate formations reveals a complex sequence of precipitation that occurred as ancient lakes and hot springs gradually dried up, leaving behind sulfate and chloride minerals that record the chemical evolution of Martian surface waters during the planet's transition from wet to arid conditions. The irony embedded in these salt flats speaks to the preservation of evidence from a dying world. The same evaporation that eliminated Mars's surface water also concentrated and preserved chemical signatures that might indicate biological activity. Jarosite, an iron sulfate mineral that forms in highly acidic environments, appears throughout the sedimentary sequence in associations that suggest hydrothermal alteration of iron-rich rocks by sulfur-bearing fluids. On Earth, jarosite formation often occurs in abandoned mine sites where sulfide minerals oxidize to produce sulfuric acid that dissolves surrounding rocks and precipitates secondary minerals in extreme pH conditions. Yet jarosite also forms in natural acid hot springs, where sulfur-oxidizing bacteria generate sulfuric acid through metabolic processes, creating environments that support specialized microbial communities adapted to pH levels that would instantly kill most terrestrial organisms. The chemical analysis of these mineral assemblages reveals trace elements that on Earth serve as micronutrients for extremophile organisms molybdenum that participates in nitrogen fixation enzymes, zinc that stabilizes protein structures in high-temperature environments, vanadium that enables alternative metabolic pathways in oxygen-limited conditions. The presence of these elements in the right chemical contexts and mineral associations provides circumstantial evidence for environmental conditions that might have supported biological activity, though their occurrence can also result from purely geochemical processes involving magmatic or hydrothermal fluids with no biological involvement. Carbonate minerals detected in association with the hydrothermal deposits tell their own story of chemical precipitation from alkaline waters that contrasted sharply with the acidic conditions recorded in sulfate-rich formations. These carbonates likely formed in separate hydrothermal systems where different water chemistry and temperature conditions created environments suitable for carbonate precipitation, possibly around neutral pH hot springs, where dissolved carbon dioxide reacted with calcium and magnesium ions to form limestone-like deposits. The coexistence of acidic and alkaline mineral assemblages within the same geological formation suggests a complex hydrothermal landscape where multiple spring systems operated simultaneously with different chemical signatures. The mineral textures preserved in these hydrothermal deposits display features that on Earth often indicate biological influence in precipitation, processes, microspheres, and filamentous structures that resemble fossilized bacterial communities, though similar features can also form through purely physical processes involving fluid flow and temperature gradients. The interpretation of these textures requires careful analysis using multiple independent techniques, from high-resolution imaging to spectroscopic identification of organic compounds that might be associated with putative biological structures. The search for biosignatures in Martian hydrothermal deposits represents one of astrobiology's most promising research directions, as these environments provide chemical energy sources that could support life even in the absence of sunlight or atmospheric oxygen. The mineral assemblages detected by Perseverance suggest that Jezero Crater once hosted hydrothermal systems comparable to those that support diverse microbial ecosystems on Earth, raising the possibility that similar communities might have colonized Martian hot springs during the planet's early history, leaving behind chemical and morphological evidence that still awaits discovery in the rocks that preserve their ancient thermal landscapes. The question of whether Mars ever hosted the molecular machinery that preceded DNA-based life leads researchers into the deepest mysteries of biochemical evolution, where RNA molecules might have served as both genetic blueprint and catalytic enzyme in primitive organisms that emerged before the complex cellular structures familiar from terrestrial biology. This hypothetical RNA world represents a transitional phase in life's origin story, when self-replicating ribonucleic acid molecules carried out the functions later divided between DNA storage systems and protein-based enzymes, creating the first chemical networks capable of evolution through natural selection and genetic inheritance. On Earth, remnants of this ancient RNA world persist in the ribosomes that synthesize proteins in every living cell, where RNA molecules still perform catalytic functions that seem to echo from biology's earliest chapters. These ribozymes demonstrate that RNA can act as both information storage system and biochemical catalyst, supporting the theoretical framework that life might have begun with RNA-based organisms before evolving the DNA-protein partnerships that characterize modern cellular biochemistry. The hypothesis gains support from laboratory experiments where RNA molecules evolve new catalytic functions under controlled conditions that simulate early Earth's chemical environment. Dr. Stephen Benner, a chemist studying the prebiotic origins of genetic systems, investigates whether the environmental conditions that existed on early Mars might have been more suitable for RNA formation than those that prevailed on early Earth. Mars's lower gravity would have allowed larger molecules to remain stable in solution, while the planet's thinner atmosphere might have provided protection from ultraviolet radiation that could damage delicate nucleotide bonds. The reduced atmospheric pressure could also have facilitated the concentration of organic precursors through evaporation cycles that alternately concentrated and diluted chemical solutions in ways that might have promoted RNA synthesis. The chemical requirements for RNA formation include not only the 4 nucleotide bases, adenine, guanine, cytosine, and uracil, but also ribose sugar and phosphate groups that link together to form the molecular backbone of genetic material. These components must assemble spontaneously from simpler precursors under conditions that allow polymerization without destroying the delicate chemical bonds that hold RNA molecules together. The process requires a delicate balance of temperature, pH, and ionic strength that permits nucleotide assembly while preventing the hydrolysis reactions that tend to break apart complex organic molecules in aqueous solutions. Martian meteorites contain organic compounds that include some of the chemical building blocks necessary for RNA synthesis. Though in concentrations far below those required for spontaneous nucleotide formation, the detection of nucleobase analogues in carbonaceous chondrites suggests that at least some prebiotic organic chemistry occurs in extraterrestrial environments, though the pathway from simple organic molecules to self-replicating genetic systems remains one of biochemistry's greatest unsolved puzzles. The irony embedded in RNA world hypotheses speaks to life's potential ubiquity and fragility if RNA-based organisms represent evolution's simplest solution to the information storage problem. They might arise readily under appropriate conditions, yet remain so vulnerable to environmental change that their signatures vanish from the geological record. The stability of RNA molecules under Martian conditions presents both opportunities and challenges for the persistence of hypothetical RNA-based life forms. The cold, dry environment might preserve nucleic acid structures for extended periods, protecting them from the thermal degradation that rapidly destroys RNA at elevated temperatures. However, the same conditions that promote molecular stability might also inhibit the metabolic processes necessary for RNA replication and evolution, creating environments where genetic material remains intact but biochemically inactive. Perseverance's instruments search for phosphorus-bearing minerals that could have provided the phosphate groups essential for RNA backbone formation. Phosphorus represents one of biology's scarcest essential elements, often limiting biological productivity in terrestrial ecosystems where phosphate availability controls the growth of microbial communities. On Mars, phosphorus occurs primarily in phosphate minerals that require specific chemical conditions for dissolution and biological uptake, suggesting that phosphorus availability might have constrained the emergence and persistence of RNA-based life forms even in otherwise suitable environments. The detection of boron-bearing minerals in Martian sediments adds another piece to the RNA world puzzle, as boron compounds can stabilize ribose sugars against decomposition reactions that would otherwise prevent nucleotide formation. Laboratory experiments demonstrate that borate minerals promote RNA synthesis by protecting sugar molecules from chemical breakdown, suggesting that boron-rich environments might have provided chemical sanctuaries where RNA polymerization could occur despite thermodynamically unfavorable conditions. The presence of borate minerals in ancient Martian lake deposits raises the possibility that chemical conditions suitable for RNA formation might have existed in specific microenvironments within larger aquatic systems. The search for RNA world remnants faces the challenge that ribonucleic acid molecules degrade rapidly under most geological conditions, breaking apart into component nucleotides and eventually into simple organic compounds that lose all trace of their former genetic function. Unlike proteins, which can leave behind amino acid signatures that persist for millions of years, RNA molecules rarely survive long enough to be preserved in sedimentary deposits except under extraordinary circumstances involving rapid burial and chemical conditions that inhibit nucleic acid hydrolysis. Yet, the possibility remains that RNA-based life forms might have left indirect evidence of their existence through metabolic products or isotopic signatures that resulted from genetic processes involving nucleic acid synthesis and degradation. The specific isotopic fractionations associated with nucleotide metabolism might create chemical fingerprints that persist in sedimentary organic matter long after the RNA molecules themselves have decomposed, providing potential biosignatures that future analytical techniques might be able to detect and interpret. The RNA world hypothesis extends the search for Martian life beyond the familiar paradigms of cellular biology to encompass more fundamental questions about the chemical origins of genetic information and metabolic catalysis. If life began with RNA-based systems before evolving the complex cellular structures observed in modern organisms, then the search for ancient life on Mars must consider the possibility that the first Martian organisms might have been radically different from anything in the terrestrial fossil record, representing alternative solutions to the basic problems of information storage, catalysis, and replication that define living systems throughout the known universe. Beneath the frozen surface of Mars, liquid water may still flow through networks of underground aquifers and hydrothermal systems, creating hidden refuges where microbial life might persist despite the hostile conditions that have sterilized the planet's exposed landscapes for billions of years. The European Space Agency's Mars Express orbiter has detected subsurface water ice deposits extending to depths of several kilometers, while ground-penetrating radar reveals layered structures that suggest liquid water tables exist at depths where geothermal heating maintains temperatures above the freezing point, despite surface conditions that average -60 degrees Celsius. The discovery of recurring slope linear dark streaks that appear and fade seasonally on crater walls and steep slopes provides tantalizing evidence that briny water might periodically reach the surface in localized seeps and springs. These features appear during warm seasons when temperatures approach the freezing point of salt water, then fade during colder periods when even concentrated brines would freeze solid. The patterns suggest that subsurface water reservoirs respond to seasonal temperature cycles, possibly through thermal expansion and contraction that drives fluid migration through fracture networks in permafrost layers. Dr. Ali Bramson, a planetary scientist studying Martian hydrogeology, models the subsurface conditions that might maintain liquid water at depths accessible to drilling technology. The calculations reveal that geothermal heat flow from radioactive decay in the planetary interior could sustain liquid water zones at depths of 1 to 2 kilometers, particularly in regions where subsurface salts lower the freezing point of water and create chemical environments similar to Earth's deep groundwater systems. These buried aquifers might harbor microbial communities that evolved from surface organisms during Mars's transition from wet to dry conditions, adapting to increasingly extreme environments as their world transformed around them. The chemical composition of Martian groundwater, inferred from mineral deposits and atmospheric measurements, suggests highly saline solutions enriched in sulfates, chlorides, and perchlorates that would challenge even the most extremophile organisms known from terrestrial environments. Yet, life on Earth thrives in equally harsh chemical conditions, from the hypersaline lakes of Antarctica to the acid mine drainage systems where bacteria derive energy from sulfur oxidation in solutions that would dissolve human tissue within minutes. These terrestrial analogs demonstrate that life can adapt to chemical extremes that seem incompatible with biological processes, suggesting that Martian groundwater might support specialized microbial communities despite its toxic chemistry. The irony, embedded in Mars's subsurface hydrology, speaks to the planet's hidden complexity, while the surface appears lifeless and static. The deep subsurface might host active hydrological systems that rival Earth's groundwater networks in scope and chemical diversity. The buried water reservoirs represent the last remnants of Mars's ancient ocean system, sequestered underground when atmospheric pressure dropped below the threshold necessary to maintain liquid water at the surface. These hidden seas might preserve not only water, but also the chemical and thermal conditions that supported life during Mars's more hospitable past. Perchlorate salts detected throughout Martian soil create both challenges and opportunities for subsurface life. These highly oxidizing compounds would be toxic to most terrestrial organisms, Yet some Earth bacteria have evolved to use perchlorates as energy sources, reducing them to chloride ions through metabolic pathways that might operate in Martian groundwater systems. The widespread distribution of perchlorates suggests that any subsurface life would need to either tolerate or actively metabolize these compounds, potentially creating distinctive isotopic signatures that might be detectable in groundwater discharge or mineral precipitates. The depth at which liquid water might exist varies with latitude and geological setting, influenced by factors including surface temperature, soil thermal properties, and the presence of subsurface heat sources such as hydrothermal circulation or residual volcanic activity. In equatorial regions where surface temperatures occasionally approach freezing, liquid water might exist at depths of several hundred meters, while in polar regions where surface conditions remain perpetually frigid, liquid zones might not occur until depths of several kilometers. These variations create a three-dimensional habitat map where potential microbial refugees cluster around geothermal anomalies and chemical environments that provide both liquid water and energy sources for metabolic processes. The search for subsurface life faces technological challenges that push the boundaries of planetary exploration capabilities. Drilling to depths where liquid water might exist requires heavy equipment that exceeds current mission mass budgets, while detecting microbial activity in buried aquifers demands analytical techniques capable of distinguishing biological signals from the complex geochemical processes that operate in subsurface environments. Future missions might employ seismic techniques to map underground water systems, or deploy autonomous drilling platforms that could penetrate permafrost layers and sample subsurface fluids directly. The temporal dynamics of Martian groundwater systems remain poorly understood, though orbital observations suggest that subsurface ice deposits undergo seasonal changes that might reflect deeper hydrological processes. During summer months, thermal models predict that warming penetrates several meters into the subsurface, potentially mobilizing brines that remain frozen during colder seasons. These thermal cycles might drive circulation patterns that transport nutrients and dissolved gases through underground aquifer systems, creating dynamic chemical environments where microbial communities could respond to seasonal variations in resource availability. The possibility of contemporary subsurface life on Mars transforms astrobiology from a historical science focused on ancient biosignatures into an active search for living organisms that might be sampled and studied directly. Such discoveries would revolutionize understanding of life's limits and distribution, demonstrating that biological processes can persist through planetary-scale environmental catastrophes and adapt to conditions far removed from those that supported life's initial emergence. The hidden biosphere beneath Mars's frozen surface might represent evolution's solution to environmental extremes that exceed anything experienced on Earth, offering insights into the forms that life might take on other worlds throughout the galaxy. The subsurface refugees that might shelter Martian microorganisms represent more than mere survival strategies. They embody the possibility that life, once established, develops the persistence and adaptability necessary to endure through cosmic time, finding ways to continue the ancient conversation between chemistry and biology even as worlds die around them. Across the rust-colored landscape of Jezero Crater, 43 sealed titanium tubes lie scattered like metallic seeds, each containing samples that Perseverance has carefully extracted from rocks that formed when Mars possessed flowing rivers and seasonal weather patterns. These cylindrical repositories, no larger than a pen yet more valuable than any terrestrial mineral, hold compressed fragments of deep, time-powdered mudstone, abraded rock surfaces, and atmospheric gases that will eventually journey to Earth aboard spacecraft still decades away from launch. The sample cache represents humanity's most ambitious attempt to bring pieces of another world home for analysis, with instruments too large and sophisticated to transport across interplanetary space. Each tube bears a unique identifier etched into its titanium surface, an alphanumeric code that links the physical sample to detailed geological context recorded in the rover's databases. Sample Jezero, collected from the delta's finest mudstone layers, contains organic compounds and mineral assemblages that might preserve evidence of ancient microbial activity, while tube Jezero holds sulfate-rich sediments from what appears to be an ancient hot spring system where hydrothermal processes concentrated, dissolved minerals through evaporation and precipitation cycles. The diverse collection represents a geological survey of Jezero Crater's most promising astrobiological targets, selected through months of careful reconnaissance and spectroscopic analysis. Meenakshi Wadhwa, principal scientist for the Mars Sample Return Mission, oversees the planning for Earth-based laboratories that will analyze these samples with analytical precision impossible to achieve on Mars. The instruments awaiting the sample's return can detect organic molecules at concentrations measured in parts per trillion, examine isotopic compositions with uncertainties smaller than the natural variations produced by biological processes, and resolve microscopic textures that might reveal fossilized cellular structures preserved in mineral matrices. These capabilities exceed those of rover-based instruments by orders of magnitude, promising insights that could finally resolve the question of whether life ever emerged on Mars. The journey home will require 2 additional spacecraft launches, a fetch rover that must locate and collect the cached samples, and an orbiting vehicle equipped with a sample containment system capable of maintaining pristine conditions during the months-long voyage to Earth. The engineering challenges involved in this interplanetary relay race push the boundaries of current space technology, requiring precise navigation, autonomous sample transfer operations, and rocket systems capable of launching from the Martian surface without contaminating the precious cargo with exhaust products or mechanical debris. The irony embedded in this patient collection process speaks to the fundamental limitations of robotic exploration. The most sophisticated instruments humanity can build remain crude compared to the analytical capabilities available in terrestrial laboratories, where researchers can dedicate months to analyzing single samples using techniques that consume more power than an entire Mars mission. The cached tubes represent a bridge across space and time, carrying chemical information from ancient Mars to present-day Earth, where human ingenuity and technological precision can unlock secrets hidden in microscopic crystal structures and molecular arrangements. Sample preservation presents unique challenges in the Martian environment, where temperature cycling and cosmic radiation could potentially alter the chemical signatures that researchers hope to study. The titanium tubes incorporate hermetic seals designed to maintain internal atmospheric composition and prevent contamination from perchlorate-rich Martian dust that could obscure organic signatures or introduce spurious chemical signals. Each seal must function perfectly despite thermal stresses that cause metal components to expand and contract through temperature ranges exceeding anything experienced by terrestrial laboratory equipment. The planned Earth-based analysis will employ techniques unavailable on Mars, including secondary ion mass spectrometry that can map isotopic compositions at microscopic scales, synchrotron X-ray spectroscopy that reveals molecular structures with atomic-level resolution, and transmission electron microscopy capable of imaging individual organic molecules preserved in mineral matrices. These instruments will search for biosignatures too subtle for rover-based detection, including amino acid chirality that might indicate biological origin, lipid biomarkers that persist in sedimentary rocks for billions of years, and mineral textures that form only through biological mediation of crystal growth processes. The sample return timeline stretches across multiple decades, with Earth-based analysis scheduled to begin in the early 2030s after successful completion of the collection and transport phases. This extended schedule reflects both the technical complexity of interplanetary sample return and the methodical pace of scientific investigation, where definitive conclusions emerge through the accumulation of evidence from multiple independent analytical techniques rather than single decisive experiments. The temporal delay ensures that the most advanced analytical instruments will be available when the samples arrive, as technological capabilities continue advancing during the mission's development and execution phases. Contamination control represents one of the mission's greatest challenges, requiring protocols that prevent terrestrial biological material from compromising the samples, while simultaneously protecting Earth's biosphere from potential Martian organisms that might survive the journey home. The samples will undergo analysis in specialized containment facilities designed for handling extraterrestrial materials, with air filtration systems and negative pressure environments that prevent any material exchange between sample containers and terrestrial laboratory environments. The geological diversity represented in the cached samples provides multiple independent tests of hypotheses about ancient Martian habitability and the potential for biosignature preservation. Samples from different stratigraphic levels record environmental conditions that spanned millions of years, while materials collected from various locations within Jezero Crater document spatial variations in chemistry and mineralogy that might reflect different ecological niches or preservation environments. This diversity ensures that negative results from individual samples will not eliminate the possibility of discovering biosignatures in other portions of the collection. The cached tubes waiting scattered across Jezero Crater represent more than scientific samples. They embody humanity's commitment to answering fundamental questions about life's distribution in the universe through patient, methodical investigation that spans decades and requires international cooperation on an unprecedented scale. Each sealed container holds the potential to transform understanding of biology's cosmic significance, to reveal whether the chemical processes that created life on Earth represent universal principles or unique accidents that occurred only once in the known universe. In the hypersaline lakes of Chile's Atacama Desert, where rainfall occurs perhaps once per decade, and salt concentrations exceed those of Earth's oceans by orders of magnitude, extremophile bacteria construct microbial mats that photosynthesize beneath protective mineral crusts and metabolize sulfur compounds in environments that serve as terrestrial analogs for the conditions that might have existed on ancient Mars. These organisms thrive in chemical conditions that would instantly kill most life forms, demonstrating evolution's capacity to colonize ecological niches that seem incompatible with biological processes, yet provide sufficient energy and chemical resources to support complex microbial communities. Dr. Natalie Cabral, an astrobiologist who studies these extreme environments as windows into possible Martian ecology, documents how life adapts to increasing aridity and chemical toxicity as climate change gradually transforms once habitable lakes into sterile salt flats. The organisms respond to environmental stress by retreating into subsurface layers where mineral precipitation creates protective barriers against ultraviolet radiation and desiccation. Developing metabolic strategies that allow survival on trace amounts of water extracted from hygroscopic salts that absorb atmospheric moisture during brief periods of elevated humidity. The evolutionary pathways that enable life to colonize extreme environments provide insight into the processes that might have allowed Martian organisms to persist through their planet's transition from wet, potentially habitable conditions to the frozen desert that exists today. Convergent evolution. The tendency for unrelated organisms to develop similar solutions to environmental challenges suggests that life elsewhere might follow predictable patterns when adapting to stress conditions such as low temperature, high salinity, and limited water availability that characterize contemporary Mars and might have affected ancient Martian ecosystems during periods of climatic deterioration. The bacterial communities in Chile's high-altitude salt lakes demonstrate remarkable tolerance for perchlorate compounds that occur naturally in these environments and dominate the surface chemistry of modern Mars. Some organisms have evolved enzymatic pathways that reduce perchlorates to chloride ions, extracting energy from chemical reactions that simultaneously detoxify their environment and provide metabolic fuel for cellular processes. These biochemical adaptations might represent evolutionary solutions that could have emerged in Martian organisms faced with similar chemical challenges, creating metabolic pathways that transform environmental toxins into energy sources. Photosynthetic organisms in extreme environments often develop protective strategies that might have applications for understanding potential Martian biology. Certain cyanobacteria produce pigments that absorb harmful ultraviolet radiation while allowing photosynthetically useful wavelengths to reach chlorophyll molecules, creating biological sunscreens that enable photosynthesis to continue, despite radiation levels that would damage unprotected cellular machinery. Similar adaptations might have evolved in Martian organisms during the period when atmospheric thinning increased surface radiation exposure, allowing photosynthetic communities to persist longer than would otherwise be possible. The irony embedded in these terrestrial extremophile studies speaks to life's unexpected resilience and creativity. The harshest environments on Earth often support the most ancient and diverse microbial communities, suggesting that extreme conditions might actually favor biological innovation rather than simply eliminating life through environmental stress. This paradox challenges assumptions about habitability and raises the possibility that Mars's transition to extreme conditions might have driven evolutionary innovation rather than simply causing mass extinction of primitive organisms. Thermophilic bacteria that thrive in hot springs at temperatures approaching the boiling point provide models for organisms that might have inhabited Martian hydrothermal systems during periods when geothermal activity maintained liquid water despite decreasing atmospheric pressure. These heat-loving microorganisms possess cellular machinery adapted to high temperatures that would denature proteins and destroy nucleic acids in mesophilic organisms, demonstrating that life can adapt to thermal extremes that occur in hydrothermal environments on both Earth and Mars. The metabolic diversity displayed by extremophile communities reveals the range of energy sources that life can exploit when conventional resources become unavailable. Chemosynthetic bacteria derive energy from the oxidation of hydrogen sulfide, methane, ammonia, and metal ions, creating food webs that function independently of photosynthesis and might persist in subsurface environments where sunlight never penetrates. These alternative metabolic pathways might have supported Martian ecosystems that retreated underground as surface conditions became increasingly hostile to biological activity. Desiccation-resistant organisms demonstrate survival strategies that might have enabled life to persist through the extended dry periods that characterized Mars's climatic history. Certain bacteria and archaea can survive complete dehydration for millions of years, entering cryptobiotic states where metabolic activity ceases, but cellular structures remain intact and capable of reactivation when water becomes available. These dormancy mechanisms might have allowed Martian organisms to survive through geological periods when liquid water disappeared from surface environments, remaining viable until hydrothermal activity or climatic changes temporarily restored habitable conditions. The study of terrestrial extremophiles reveals that life's limits extend far beyond the conditions that characterize Earth's temperate biosphere, encompassing temperature, pressure, pH, and chemical ranges that overlap with environmental conditions inferred for ancient and contemporary Mars. This overlap suggests that, if life ever emerged on Mars, it might have possessed the evolutionary flexibility necessary to adapt to changing conditions rather than simply succumbing to environmental deterioration as the planet lost its atmosphere and surface water. The convergent evolution observed in extreme environments provides a framework for predicting the characteristics that Martian life might have developed in response to environmental challenges unique to that planet. The biochemical solutions that terrestrial organisms have evolved for surviving in Mars-like conditions, from perchlorate metabolism to radiation resistance to desiccation tolerance, might represent universal adaptive strategies that would emerge independently in any biological system faced with similar environmental pressures. These terrestrial analogues transform the search for Martian life from an exercise in detecting familiar biological signatures into a broader investigation of the forms that life might take when pushed to the extremes of chemical and physical tolerance, suggesting that the universe might harbor biological diversity that far exceeds anything present in Earth's moderate environments, where most research has focused throughout the history of biological science. In the sterile laboratories of NASA's Johnson Space Center, pristine chambers equipped with laminar flow hoods and positive pressure systems await the arrival of Martian samples that will undergo analysis with instruments capable of detecting organic molecules in concentrations measured in parts per quadrillion sensitivities that approach the theoretical limits of analytical chemistry. These facilities, designed specifically for extraterrestrial sample analysis, incorporate contamination control protocols more stringent than those used in semiconductor manufacturing or pharmaceutical production, ensuring that terrestrial biological material cannot compromise the chemical signatures that researchers hope to find preserved in rocks that crystallized on an alien world billions of years ago. The planned analytical sequence will begin with non-destructive techniques that preserve sample integrity while providing initial characterization of mineralogy, morphology, and chemical composition. X-ray computed tomography will map internal structures at microscopic resolution, revealing grain boundaries, fracture patterns, and mineral distributions that might indicate biological influence in rock formation processes. Raman spectroscopy will identify organic compounds and their molecular structures without consuming sample material, creating chemical inventories that guide subsequent destructive analyses toward the most promising targets for biosignature detection. Dr. Francis Westall, an expert in early life biosignatures, studies the analytical challenges involved in distinguishing between biological and geological organic matter in samples that have undergone billions of years of thermal and chemical alteration. The techniques she employs on Earth's oldest rocks, including two-step laser desorption, mass spectrometry, and nanoscale secondary ion mass spectrometry, will be adapted for Martian sample analysis, providing isotopic and molecular data with precision sufficient to detect the subtle chemical fingerprints that biological processes leave in sedimentary organic matter even after extensive geological processing. The laboratory protocols account for the possibility that Martian organic compounds might display chemical and isotopic signatures unlike anything found in terrestrial biological systems, requiring analytical flexibility that can accommodate unfamiliar biochemistries while maintaining the rigorous standards necessary for distinguishing biological from non-biological processes. Comparative studies using synthetic organic compounds and abiotic synthesis experiments will establish baseline signatures for non-biological organic matter formation, providing reference standards against which Martian samples can be evaluated. Transmission electron microscopy will search for microscopic structures that might represent fossilized cellular remains, examining sample thin sections at magnifications capable of resolving features smaller than bacterial ribosomes. The technique requires careful sample preparation that preserves original textures while creating sections thin enough for electron beam transmission, a process that consumes minute amounts of irreplaceable sample material but provides morphological data unavailable through any other analytical approach. Each microscopic image will undergo intensive analysis to distinguish between genuine biosignatures and mineral textures that might mimic biological structures through purely geological processes. The irony embedded in this analytical approach speaks to the fundamental challenge of astrobiology. The most definitive evidence for ancient life often exists at scales below the resolution of even sophisticated instruments, requiring researchers to build circumstantial cases based on the accumulation of compatible evidence rather than single decisive observations. The search for Martian biosignatures will proceed through the patient correlation of isotopic, molecular, and morphological data, seeking patterns that collectively point toward biological activity while individually might admit alternative explanations. Synchrotron radiation facilities will provide X-ray beams millions of times brighter than conventional laboratory sources, enabling spectroscopic analysis of trace organic compounds embedded within mineral matrices that would be impossible to extract and purify using conventional techniques. These intense X-ray sources can map the spatial distribution of organic molecules within rock samples, revealing whether carbon-bearing compounds occur in patterns consistent with biological concentration mechanisms or geological precipitation processes. The analysis requires travel to specialized facilities where samples must be transported under strict containment protocols that prevent contamination or loss of precious material. Isotopic analysis will employ techniques capable of measuring carbon, sulfur, and nitrogen isotope ratios with uncertainties smaller than the natural variations produced by biological fractionation processes. These measurements require careful correction for isotopic changes that might have occurred during sample collection, transport, and laboratory processing, ensuring that any biological signatures remain distinguishable from analytical artifacts or terrestrial contamination. Multiple independent isotopic measurements will cross-validate results and build confidence in interpretations that might revolutionize understanding of life's cosmic distribution. The analytical timeline extends across multiple years as research teams apply increasingly sophisticated techniques to samples that prove most promising during initial screening procedures. Each analytical campaign will consume small portions of irreplaceable sample material, requiring careful planning to ensure that sufficient material remains available for future techniques that might be developed during the extended analysis period. The methodical approach reflects both the precious nature of the samples and the recognition that extraordinary claims require extraordinary evidence supported by multiple independent lines of investigation. Quality assurance protocols will include blind sample analyses, where researchers examine terrestrial materials and synthetic standards without knowing their origins, establishing baseline error rates and demonstrating that analytical techniques can reliably distinguish between biological and non-biological signatures under controlled conditions. These validation studies will continue throughout the Martian sample analysis program, providing ongoing verification that positive results reflect genuine scientific discoveries rather than analytical artifacts or contamination events. The laboratory investigations will generate terabytes of analytical data that require sophisticated computational analysis to identify patterns and correlations that might not be apparent in individual measurements. Machine learning algorithms will search for subtle signatures that human analysts might overlook, while statistical techniques will quantify the probability that observed patterns result from biological rather than geological processes. The computational analysis represents a form of digital archaeology, seeking evidence of ancient life in multidimensional datasets that encode chemical information from rocks that formed when Mars was young and possibly alive. The quiet laboratory where these analyses will unfold represents humanity's most sophisticated attempt to answer one of the most profound questions ever posed: did life emerge independently on Mars? Or does biology represent a unique accident that occurred only once in the known universe? The answer, if it comes at all, will emerge slowly from the patient accumulation of evidence, from measurements so precise they approach the fundamental limits of analytical chemistry, from the methodical work of scientists who understand that the universe reveals its secrets only to those who ask the right questions with sufficient care and persistence. 4.5 billion years ago, both Mars and Earth coalesced from the same disk of dust and debris that surrounded the young sun, inheriting similar inventories of water, organic compounds, and the chemical elements necessary for life's emergence. Yet following divergent evolutionary pathways that led one world toward biological complexity, while the other descended into frozen sterility, the parallel formation histories reveal how subtle differences in planetary mass, orbital distance, and magnetic field strength can determine whether worlds develop into cradles of life or remain barren monuments to missed opportunities. Their surfaces sculpted by geological forces but never animated by the chemistry of living organisms. During the late heavy bombardment, approximately 4 billion years ago, both planets endured intense cosmic bombardment as gravitational perturbations in the outer solar system sent asteroids and comets careening toward the inner planets in a celestial artillery barrage that lasted hundreds of millions of years. These impacts delivered water and organic compounds to both worlds, while simultaneously sterilizing surface environments through shock heating that vaporized oceans and created molten seas of rock that persisted for thousands of years after individual impact events. The bombardment represented both opportunity and catastrophe, providing the raw materials for life while creating conditions that would destroy any biological systems that managed to emerge during the chaos. Dr. Timothy Lyons, a geochemist studying Earth's earliest biosphere, examines how both planets might have developed similar environmental conditions during the Archean era, when reducing atmospheres rich in methane and hydrogen created greenhouse warming despite the sun's lower luminosity during its early evolutionary phases. The atmospheric chemistry that prevailed on both worlds would have favored the formation of organic compounds through photochemical reactions involving methane, carbon dioxide, and nitrogen, creating chemical inventories that might have supported prebiotic evolution and the emergence of self-replicating molecular systems on both planets simultaneously. The magnetic field histories of both worlds reveal critical differences that ultimately determined their divergent fates. Earth's larger mass enabled the maintenance of vigorous convection in its iron core, sustaining a magnetic dynamo that has operated continuously for billions of years and provided protection from solar wind erosion throughout the planet's biological evolution. Mars, being smaller and cooling more rapidly, lost its global magnetic field sometime between 3 and 4 billion years ago. leaving its atmosphere vulnerable to stripping by charged particles that gradually eroded the greenhouse gases necessary for maintaining liquid water at the surface. Evidence from both planets suggests that impact events during the late heavy bombardment might have created similar hydrothermal systems where heated groundwater circulated through fractured crustal rocks, creating chemical conditions that could have supported the origin of life through mineral-catalyzed organic synthesis reactions. These impact-generated hydrothermal systems might have persisted for millions of years after individual crater-forming events, providing stable environments where biological processes could emerge and evolve despite the chaotic conditions that characterize the early solar system. The irony embedded in this comparative planetary evolution speaks to the contingent nature of biological development. Earth and Mars began with similar potential for supporting life, yet small differences in planetary properties led to dramatically different outcomes over geological timescales. The two worlds serve as natural experiments in planetary habitability, demonstrating how astronomical factors beyond terrestrial control, planetary mass, orbital distance, magnetic field strength determine whether worlds develop the long-term stability necessary for biological evolution to proceed from simple chemistry to complex ecosystems. Isotopic evidence from both planets suggests that water delivery occurred through similar processes involving cometary and asteroidal impacts that continued long after initial planetary accretion. The deuterium to hydrogen ratios measured in Martian atmospheric water vapor and terrestrial oceanic water indicate partially overlapping source regions in the outer solar system, though the precise mixing ratios differ between the two worlds in ways that reflect their different impact histories and atmospheric evolution pathways. These isotopic signatures provide windows into the early solar system's dynamics and the processes that distributed water throughout the inner planetary region. Volcanic outgassing on both planets contributed to early atmospheric development, releasing water vapor, carbon dioxide, and sulfur compounds that accumulated in primordial atmospheres and provided the chemical foundations for subsequent atmospheric evolution. The volcanic activity that characterized both worlds during their first billion years created reducing environments where organic synthesis reactions could proceed despite the absence of biological catalysts, potentially creating chemical precursors that later served as starting materials for biological evolution when environmental conditions became suitable for life's emergence. The stratigraphic records preserved on both planets document the transition from impact-dominated early histories to more stable environmental conditions that allowed sedimentary processes to operate without constant disruption from cosmic bombardment. On Earth, this transition coincided with the emergence of the first bacterial communities that began modifying atmospheric chemistry through metabolic processes. While on Mars, the same period might have witnessed the emergence of life that subsequently went extinct as environmental conditions deteriorated beyond the limits of biological tolerance. The comparative study of Martian and terrestrial geology reveals how planetary size influences the duration of geological activity and the maintenance of habitable surface conditions. Earth's larger mass enabled sustained volcanic activity and plate tectonics that continue recycling crustal materials and regulating atmospheric composition through carbonate-silicate cycles, while Mars's smaller size led to earlier cessation of major geological processes and the gradual deterioration of surface habitability as internal heat sources became insufficient to drive atmospheric regulation mechanisms. Contemporary research on both planets focuses on understanding the environmental thresholds that determine planetary habitability and the timescales over which worlds can maintain conditions suitable for biological activity. The search for ancient life on Mars provides crucial data for understanding whether biological emergence represents a probable outcome of planetary evolution under appropriate conditions, or whether Earth's biosphere represents an extraordinary accident that occurred despite overwhelming odds against biological development in cosmic environments dominated by chaos and extremes. The intertwined histories of Mars and Earth continue unfolding through robotic exploration that extends human consciousness across interplanetary space, seeking evidence of ancient biological activity that might reveal whether life represents a universal response to appropriate chemical and physical conditions, or whether the universe remains fundamentally hostile to the emergence of complex organized matter capable of evolution. Reproduction. and the kind of chemical creativity that transforms dead worlds into living planets. The question that drives humanity's robotic exploration of Mars unfolds with the patience of geological time, emerging not from single decisive discoveries, but through the gradual accumulation of evidence that slowly constrains the possibilities for ancient life on a world that died before complex organisms learned to inhabit Earth's oceans. Each measurement transmitted from Perseverance's instruments adds another data point to a vast matrix of chemical, isotopic, and morphological information that researchers analyze with statistical techniques designed to distinguish between the subtle signatures of biological activity and the background noise of purely geological processes that can mimic life's chemical fingerprints with remarkable fidelity. The scientific method demands extraordinary evidence for extraordinary claims, requiring researchers to exhaust alternative explanations before concluding that observed phenomena result from biological rather than geological processes. The organic compounds detected in Martian sedimentary rocks could originate from meteoritic delivery, volcanic outgassing, or high-temperature synthesis reactions that produce complex carbon chemistry without biological involvement. The isotopic signatures that might indicate metabolic fractionation could also result from thermal processing, atmospheric photochemistry, or mineral precipitation processes that concentrate lighter isotopes through purely physical mechanisms. Dr. David Beatty, who coordinates international planning for Mars exploration missions, emphasizes that definitive evidence for ancient Martian life will likely emerge through the convergence of multiple independent lines of investigation rather than through single breakthrough discoveries that resolve all uncertainties. The case for biological activity must be built through the patient correlation of organic geochemistry, mineral textures, isotopic compositions, and morphological features that collectively point toward biological influence, while individually might admit alternative interpretations that require careful consideration and systematic elimination. The temporal scales involved in this investigation span from the microsecond precision of analytical measurements to the billion-year timescales over which geological processes operate and biological signatures might be preserved or destroyed. Each sample analysis represents a moment of contact between human curiosity and cosmic deep time, where sophisticated instruments probe the atomic structure of materials that formed when the solar system was young and chaotic, searching for evidence of chemical processes that might have operated for brief intervals during Mars's early history before environmental conditions became unsuitable for biological activity. The uncertainty that surrounds current evidence reflects the fundamental challenge of interpreting ancient processes through their degraded remnants, where billions of years of thermal cycling, radiation exposure, and chemical alteration have modified original signatures in ways that obscure their origins and complicate scientific interpretation. The organic molecules detected by Perseverance might represent the altered remains of once abundant biological materials, or they could be the products of abiotic synthesis reactions that occurred during hydrothermal processing of carbonaceous meteoritic materials that accumulated in ancient lake sediments. Future missions will refine analytical capabilities and expand the geographical scope of sample collection, seeking convergent evidence from multiple locations and geological contexts that might strengthen or weaken the case for ancient Martian biology. The planned sample return missions represent humanity's most ambitious attempt to bring pieces of another world home for analysis with instruments that exceed current rover capabilities by orders of magnitude, providing isotopic precision and molecular sensitivity that might finally resolve ambiguities that current data cannot address definitively. The irony embedded in this patient search speaks to the nature of scientific discovery itself. The most profound questions often yield their answers slowly through the methodical accumulation of evidence rather than through dramatic revelations that instantly transform understanding. The search for ancient life on Mars proceeds through the careful correlation of subtle signals that hover at the threshold of analytical detection, requiring researchers to balance skepticism with openness to possibilities that might revolutionize understanding of life's cosmic significance and distribution. The broader implications of Martian life detection extend far beyond the immediate scientific question to encompass fundamental issues about biology's universality and the probability that life emerges elsewhere in the universe under appropriate conditions. A positive result would suggest that biological processes represent probable outcomes of chemical evolution when suitable environments persist for sufficient time, while negative results might indicate that life's emergence requires extraordinary circumstances that rarely align in cosmic environments dominated by chaos and extreme conditions. The search continues with mechanical persistence across landscapes that preserve chemical information from epochs when Mars might have hosted the molecular processes that bridge the gap between geology and biology. Each sol brings new measurements that add to the growing database of evidence. Each sample contributes to the statistical foundation upon which future conclusions will rest. Each observation participates in humanity's greatest detective story, the investigation of whether life represents a cosmic phenomenon or a terrestrial accident that occurred only once in the known universe. The answer, when it comes, will emerge from the patient work of scientists who understand that the universe reveals its secrets only to those who ask questions with sufficient precision and persistence. The robotic explorers that traverse Martian landscapes carry more than analytical instruments. They bear humanity's deepest curiosities about the nature of life itself, about the chemical possibilities that exist in cosmic environments, about the forms that biology might take when pushed to extremes that exceed anything experienced on Earth. The quiet conversation between human ingenuity and cosmic mystery continues across the radio silence of interplanetary space, where data streams carry chemical information from ancient Mars to laboratories where researchers bend over computer screens and instrumental printouts, searching for patterns that might indicate whether the red planet once knew the chemistry of life or whether Earth remains unique in harboring the complex molecular processes that transform dead matter into living systems capable of wonder. Curiosity. And the patient search for truth among the stars. The silence of Jezero Crater settles like dust across the ancient delta where perseverance rests between sols, its instruments powered down and its mechanical systems cycling through thermal hibernation protocols that preserve battery life through the long Martian nights. The samples it has collected sleep in titanium tubes scattered across the landscape, each container holding compressed fragments of deep time that will eventually journey to Earth aboard spacecraft that exist only as blueprints in engineering laboratories where teams of specialists plan missions that span decades of patient development and international cooperation. The questions that drive this exploration echo across the vacuum of space at light speed, carrying human curiosity toward a world that may once have harbored the chemistry of life, but now preserves its secrets in mineral assemblages and isotopic signatures that hover at the threshold of analytical detection. The search for ancient biology proceeds with the methodical pace of geological investigation, where definitive answers emerge through the accumulation of evidence rather than single decisive discoveries that instantly resolve cosmic mysteries. In laboratories on Earth, researchers continue analyzing data transmitted from Mars, building statistical models that correlate organic geochemistry with environmental conditions, searching for patterns that might distinguish between biological and geological processes in rocks that formed when the solar system was young. The work proceeds with mechanical patience, each measurement adding to a growing database of chemical information that future scientists will use to constrain theories about life's emergence and distribution throughout the universe. The red planet continues its ancient orbit around a sun that burns slightly brighter than it did 4 billion years ago, when Mars might have possessed thick air and flowing water that supported microbial communities in environments that now lie exposed to cosmic radiation and temperature extremes. The world spins through days and seasons with clockwork regularity, its frozen landscapes preserving evidence of climatic transitions that transformed a potentially habitable planet into the sterile monument that greets human exploration with silence and mystery. Time moves differently on Mars than on Earth, measured not in heartbeats, but in the slow decay of radioactive elements, not in seasons, but in orbital cycles that stretch across years of terrestrial time. The patience required for interplanetary exploration mirrors the geological timescales that created the rocks under investigation, where answers emerge slowly from the methodical application of scientific techniques to materials that have waited billions of years for analysis. The search for life beyond Earth represents more than scientific curiosity. It embodies humanity's deepest questions about existence itself, about the chemical possibilities that operate in cosmic environments, about the forms that biology might take when conditions permit the emergence of self-replicating molecular systems capable of evolution and adaptation. The answer, when it comes, will emerge from the patient accumulation of evidence, from measurements so precise they approach the theoretical limits of analytical chemistry. Sleep well. Travelers across time and space, knowing that the conversation between human curiosity and cosmic mystery continues in the silence between radio transmissions, in the patient work of instruments that measure chemical compositions with digital precision, in the dreams of scientists who dedicate their lives to understanding whether Earth's biosphere represents a unique accident or a probable outcome of chemical evolution under appropriate conditions. The universe keeps its secrets well, but yields them eventually to those who listen with sufficient care and patience.